All right, so let's dive into something pretty foundational today.
Okay.
Jan LeCun's 1998 paper,
Okay.
Gradient-Based Learning Applied to Document Recognition.
Right.
Now, you might be thinking,
Yeah.
1998,
Mm-hmm.
isn't that ancient history when it comes to AI?
Yeah, you could say that.
And yeah, you're not wrong.
Right.
But this paper is like the foundation upon which modern deep learning, especially in image recognition,
Yeah.
is built.
It's fascinating how, even though this research was published over 25 years ago,
Right.
it introduced so many concepts that are still
Yeah.
at the heart of how we build AI systems today.
It's like we're peeking into the workshop where the first self-driving car was dreamt up.
Yeah.
So in this deep dive, we're going to break down what LeCun and his team achieved.
Okay.
We'll unpack the architecture of their early convolutional neural network,
All right.
LeNet-5,
Mm-hmm.
understand why it was so revolutionary,
Okay.
and see how its legacy continues to shape AI today.
And to really appreciate the impact, we have to remember the context.
Yeah,
Back in 1998,
right.
the idea of using neural networks to tackle complex tasks, like recognizing handwritten characters,
Right.
was still pretty fringe.
It wasn't the AI gold rush we see today.
Not at all.
So could you walk us through what LeNet-5 actually looks like under the hood?
Sure. So imagine a digital assembly line for processing images.
Okay.
LeNet-5 is built as a series of steps.
Yeah.
First, you have convolutional layers.
Mm-hmm.
Think of them like specialized filters.
Okay.
They scan the image looking for specific features,
Okay.
like edges or corners.
So instead of looking at the entire image all at once,
Yeah.
it's breaking it down into these smaller, more manageable chunks.
Exactly. And here's the key insight.
Yeah.
As you stack these convolutional layers, the network starts to learn
Yeah.
progressively more complex features.
Mm-hmm.
The first layer might just detect simple edges,
Right.
but later layers can recognize patterns formed by those edges, like circles or squares.
It's almost like the network is building up an understanding of the image layer by layer. Kind of like how we learn, starting with simple building blocks and then moving to more complex concepts.
That's a great analogy.
Okay.
Now, after these convolutions, we have something called subsampling or pooling layers.
Okay.
Think of this as like shrinking a high-resolution photo down to a smaller size. You're keeping the important information, the overall shapes and patterns,
Right.
but discarding some of the fine details.
So you're basically summarizing the image,
Exactly.
right? Keeping the key points and ditching the fluff.
Mm-hmm.
But why is this important for LeNet-5?
So this summarizing, which we call dimensionality reduction,
Okay.
is crucial for two reasons.
Right.
First, it makes the network more robust.
Okay.
Minor variations in the input image, like slight rotations or shifts, won't throw it off as much.
Okay.
And second, it prevents the network from getting bogged down in too much detail,
Right.
which speeds up processing and makes training more efficient.
So it's about finding that sweet spot
Yeah.
between retaining important information and keeping things manageable.
Exactly.
So we've got our image broken down into these essential features.
Right.
What happens next?
This is where the magic of neural networks really kicks in.
Good.
These extracted features are then fed into a series of fully connected layers.
Okay.
This part is similar to a classic neural network,
Mm-hmm.
where each layer combines the information from the previous layer
Right?
to ultimately make a prediction.
Okay.
In this case, the prediction is what character the image represents.
So all these layers work together like a chain reaction, transforming a raw image into a classification.
Yeah.
It's fascinating how this whole process mimics,
Right.
in a very simplified way,
Yeah.
how our own brains might process visual information.
And the beauty of LeNet-5
Yeah.
is that it actually works.
Well, that's good.
Using a technique called backpropagation, the network learns from its mistakes
Right.
and adjusts its internal parameters to improve its accuracy over time.
The backpropagation sounds a bit intimidating. What's actually happening during this learning process? Is it like the network is being scolded for getting the wrong answer?
Not quite scolding,
Oh, no.
but you're on the right track.
Okay.
Imagine you're learning to throw darts.
All right.
At first, you might miss the target completely,
Sure.
but with each throw, you adjust your aim based on where the dart landed.
Right.
Backpropagation is like that feedback loop,
Okay.
allowing the network to fine-tune its parameters based on the errors it makes.
So it's constantly refining its aim,
Exactly.
getting better and better with each try.
Yep.
That
Yeah.
makes sense.
But like anything new, there are probably some challenges along the way.
For sure.
Absolutely.
What were some of those?
One of the biggest hurdles they had to overcome
Yeah.
was something called the vanishing gradient problem.
Okay.
This occurs when the error signals used to train the network get weaker and weaker as they travel back through the layers.
Okay.
It's like playing a game of telephone, where the message gets distorted with each retelling.
That sounds like it could really throw a wrench in the whole learning process.
Exactly.
Yeah.
And it was a major obstacle in the early days of deep learning.
I bet.
But LeCun and his team came up with some clever workarounds.
Okay.
Like carefully initializing the network's weights, using a technique called pre-training.
Okay.
Yeah.
So it's like giving the network a head start.
Precisely.
Right. Making sure those error signals don't get lost in translation.
Exactly.
Yeah, okay, cool.
Yeah. This pre-training helps to ensure that the gradients are propagated more effectively throughout the network, allowing those early layers to learn properly. But beyond the technical ingenuity, what's truly impressive is how LeCun and his team meticulously evaluated LeNet-5's performance. They didn't just rely on a single metric. They really put it through its paces.
It's like they weren't just satisfied with building a car, they wanted to make sure it could handle any terrain.
Exactly. And they weren't afraid to compare LeNet-5 to other approaches, including traditional machine learning methods and other types of neural networks. They pitted it against algorithms like K-nearest neighbor support vector machines, even a simpler convolutional network called LeNet-1.
So it was like a deep learning showdown. Did LeNet-5 emerge as the undisputed champion?
Across a range of experiments and datasets, LeNet-5 consistently outperformed the other methods. It achieved lower error rates and showed a remarkable ability to generalize, which means it could accurately recognize characters it hadn't seen during training.
That's what really separates the contenders from the pretenders. It's one thing to memorize the answers, but true intelligence lies in being able to adapt to new situations. But hold on, back in the 90s, wasn't computing power a major limitation? How did they manage to train such a complex network with the technology available back then?
That's a great question. Computational resources were indeed much more limited compared to what we have today. But LeCun and his team were incredibly resourceful. They optimized their algorithms, experimented with different hardware configurations, and even employed clever tricks to make the training process more efficient.
It's like they were master chefs working with a limited pantry but still managing to create a culinary masterpiece. And the impact of their work was huge, right? It wasn't just about recognizing digits. LeNet-5 really paved the way for the deep learning revolution we see today.
Absolutely. The success of LeNet-5 demonstrated that deep neural networks, despite the challenges of training them, could achieve remarkable results on complex tasks. It reignited interest in neural networks, inspired a whole new generation of researchers, and ultimately laid the groundwork for breakthroughs in fields like computer vision, natural language processing, and even self-driving cars.
It's mind-blowing to think about how this one paper, published before smartphones or social media even existed, sparked such a technological revolution. But it wasn't just about celebrating success. They also acknowledged the limitations of their approach and highlighted some of the challenges that lay ahead for the field.
You're right. They weren't afraid to point out the open problems and future directions for research. For example, they emphasized the need for a better understanding of the learning process in deep networks. How exactly do these networks learn such complex representations? What are the limitations of current training algorithms? These are questions that still occupy researchers today.
It reminds me of how early explorers would map out new territories, not just marking the known lands, but also indicating the uncharted areas ripe for discovery.
A perfect analogy. And they also highlighted the need for more robust and efficient training methods. Remember, they were working with significantly limited computational power. They anticipated the need for scalable training algorithms that could handle even larger datasets and more complex tasks.
So they were already thinking about the future, envisioning a world where deep learning could tackle even more ambitious challenges. But let's bring it back to the paper's focused document recognition. LeNet-5 was primarily designed for recognizing individual characters. What about recognizing entire words or sentences, especially in handwritten documents? Surely that introduces a whole new level of complexity.
You're absolutely right. Recognizing sequences of characters brings in the element of time or order. The network not only needs to identify individual characters, but also understand their relationships and context within a sequence.
It's like the difference between recognizing individual letters and actually reading a word.
Yeah.
You need to understand how the letters fit together to make sense of it.
Exactly. And this temporal aspect adds a whole new dimension to the problem. They also highlight the challenge of segmentation, which is separating individual characters or words within a handwritten document. Handwriting can be messy with characters overlapping or having poorly defined boundaries. It's not always clear where one character ends and another begins.
That makes sense.
Yeah,
It's like trying to decipher a message scribbled on a napkin after a wild night out.
that's a vivid image. And this ambiguity can create problems for recognition systems. They need to be robust enough to handle these variations and accurately segment the input.
So we're not just dealing with neatly printed characters anymore. It's the Wild West of human handwriting. But surely they had some ideas for how to tackle these new challenges. Did they have a secret weapon up their sleeve?
They did. And this is where things get really interesting. They introduced the concept of graph transformer networks, specifically designed to handle sequential data, like strings of characters or words. Does that ring a bell?
Graph transformer networks. Wait a minute, are those related to the transformer networks that are all the rage in AI these days? The ones powering things like ChatGPT and language translation?
You got it. LeCun's work on graph transformer networks was a precursor to the modern transformer architectures that have revolutionized fields like natural language processing and machine translation.
Wow. It's like they were planting the seeds for an AI revolution that would blossom decades later. But can you break down how these graph transformer networks work? What makes them so special for handling sequences?
Unlike traditional neural networks that process data in a fixed order, step-by-step graph transformer networks can dynamically adjust the order in which they attend to different parts of the input sequence.
So they're not just marching through the sequence like a robot. They can jump around and focus on different parts as needed. That's pretty clever. But how does this help with something like recognizing handwritten words?
Imagine trying to read a handwritten word where some of the letters are smudged or illegible. A graph transformer network can learn to focus on the clearer letters first, using their context to infer the missing or ambiguous parts.
So it's like a detective piecing together clues from a crime scene, using the available evidence to fill in the gaps.
Exactly. And this ability to handle context and variability is what makes graph transformer networks so powerful for document recognition and other sequential tasks.
This is all mind-blowing stuff.
Mm-hmm.
But I have to admit, I'm still a bit fuzzy on how these graph transformer networks actually process a sequence. Could you give us a more concrete example?
Sure. Let's take the handwritten word hello. A graph transformer network would first represent each letter as a node in a graph.
Okay, so each letter gets its own little node. What happens next?
The network then learns to compute relationships or connections between these nodes. Essentially, it figures out how the letters are related to each other in the sequence.
So it's like drawing lines between the nodes to show how they're connected, like a family tree of letters.
Precisely. And these connections can encode all sorts of information: the order of the letters, their relative positions, even their visual similarities. It's not just treating each letter as an isolated entity, it's understanding how they fit together to form a meaningful word.
So it's like the network is building a mental model of the word, taking into account both the individual letters and their relationship.
Exactly. And this holistic representation allows the network to make more accurate predictions, even when some parts of the sequence are noisy or unclear.
That's an incredibly elegant solution. But before we get too carried away with graph transformers, maybe we should give our listeners a moment to catch their breath. We've covered a lot of ground today, from the nuts and bolts of Linux 5 to this mind-bending concept of graph transformer networks. We'll be back in a jiffy to explore the lasting legacy of LeCun's work and how his vision continues to shape the world of AI. And we're back for the final part of our deep dive into Yann LeCun's groundbreaking paper.
All right.
It's amazing to think
Yeah.
that so much of what we take for granted in AI today has its roots in this 1998 research.
It really highlights how these fundamental discoveries in science can have a ripple effect, influencing entire fields for decades.
Totally. And one of the things that struck me in this paper was their emphasis on the importance of hierarchical representations.
Okay.
They weren't just satisfied with recognizing characters in isolation.
Right.
They wanted to understand how these characters combine to form words, sentences, and ultimately meaning.
They recognize that true document recognition goes beyond individual characters.
Right.
It's about understanding the structure and context of the whole document.
It's like saying that recognizing individual musical notes is just the beginning.
Right.
To truly appreciate music,
Yeah.
you need to understand how those notes come together to create melodies, harmonies,
Yeah.
and a complete composition.
That's a great analogy.
So how do they go about achieving that?
Well, they introduced this concept of composing simpler modules into more complex systems.
Okay.
Imagine a hierarchy of recognition modules, each specializing in a particular level of abstraction.
So we have these specialized modules,
Yeah.
each with its own expertise.
Right.
How do they all work together?
Through a process they called graph composition,
Okay.
the output of one module becomes the input to the next,
Right.
gradually building up a more sophisticated representation of the document.
So it's like an assembly line
Mm-hmm.
where each station adds a new component, eventually resulting in a finished product.
Exactly.
Now, this hierarchical composition allows the system to tackle these increasing levels of complexity.
Yeah.
But how do you make sure that all these modules are working together smoothly?
That's where the idea of a global control mechanism comes in.
Okay.
They propose a central unit that oversees the entire system,
Right.
deciding which modules to activate
Okay.
and how to combine their outputs based on the specific document being analyzed.
So it's like the conductor of an orchestra,
Yeah,
making sure all the musicians are in sync and following the score.
exactly.
That makes sense.
This global control unit is crucial for ensuring the system functions as a cohesive whole,
Right.
making intelligent decisions about how to interpret the document.
This hierarchical modular approach is remarkable.
It really is.
It seems like they were decades ahead of their time
Mhm.
thinking about how to build complex AI systems.
Absolutely. And this idea of composing simpler modules into more sophisticated systems has had a profound impact on AI, especially in areas like robotics and natural language processing.
It's as if they provided the blueprint for building intelligent machines way back in 1998.
Yeah.
But it's important to remember this paper wasn't just about grand visions.
Right.
It was also about practical applications and real-world results.
Absolutely. They dedicated a significant portion of the paper
Yeah.
to demonstrating how these ideas could be implemented and tested
Okay.
on actual document recognition tasks.
So they rolled up their sleeves and proved these concepts could work in the real world.
Exactly.
What were some of the tasks they tackled?
They applied their system to a range of challenges,
Okay.
from recognizing handwritten digits to processing bank checks and even deciphering postal addresses.
That's quite a variety.
Yeah.
And how did their system perform on these real-world tasks?
Well, according to their results,
Yeah?
the system achieved impressive accuracy rates
Okay.
across these different tasks.
That's awesome.
They successfully demonstrated the power of their modular hierarchical approach,
Right.
even when dealing with noisy and challenging data sets.
It shows they weren't just theorizing.
Mm-hmm.
They were building systems that could make a real difference.
Exactly. And this emphasis on practical applications is a hallmark of LeCun's work.
Yeah.
He's not just interested in advancing AI for the sake of it.
Right.
He wants to see these technologies used to solve real-world problems.
It's a powerful reminder that AI is about more than just algorithms.
Yeah.
It's using those algorithms to have a positive impact on the world.
I completely agree. And that's a big part of why LeCun's work has been so influential.
Right.
He's a true pioneer
Yeah.
who not only deepened our understanding of deep learning,
Mm-hmm.
but also inspired countless others to apply these technologies to real-world challenges.
Well, I think that's a fantastic note to wrap up our deep dive.
Yeah.
We've explored so much
We have.
from the intricacies of Linnet 5's architecture to the grand vision of hierarchical modular AI systems. And we've seen how LeCun's work has shaped the landscape of AI, paving the way for the incredible advancements we see today.
It's been a fascinating journey through the history of deep learning
It has.
and a testament to the power of innovative ideas to transform the world.
Before we sign off, I want to leave our listeners with a final thought.
Okay.
LeCun's paper focused on character recognition,
Right.
but the techniques and ideas he presented have much broader applications.
Yeah.
Imagine adapting these concepts to recognize not just characters, but entirely different types of patterns or objects.
It's interesting.
What incredible possibilities does that unlock?
A lot.
And as we develop these increasingly powerful AI systems,
Right.
what ethical considerations should we keep in mind?
For sure.
I encourage all of you to ponder these questions
Yeah.
and continue exploring the vast and ever-evolving world of AI. Until next time, happy diving.